I'm Lauren Zarzar. I'm an assistant professor in the Department of Chemistry, and I have a courtesy appointment in the Department of Materials Science and Engineering. I have all of my undergraduate and graduate degrees are in chemistry. I also studied economics as an undergrad. So my graduate work was actually studying responsive materials and hydrogel actuators in microscale stimuli responsive smart materials. And then I did my postdoc looking at droplets and emulsions and multi-phase fluids. And now in my group here at Penn State, we're really interested in studying dynamics of microscale materials, where we're trying to understand liquids and polymers and soft materials that interfaces, how to make materials that are adaptive, responsive, interact, communicate with each other. We're also doing some work with laser writing, where we're using lasers to synthesize and pattern in inorganic and organic nanomaterials.
So when did you know chemistry would be your primary field of study? And was there like a specific class or experience or anything that helped you decide for this?
It's hard for me to pinpoint the precise time when I knew I was going to study chemistry. Ever since I was young, I loved science. I actually thought I was going to be a marine biologist when I was young. I loved reading books about the ocean and dolphins and marine life. So I always thought I was going to be a marine biologist. I got to middle school and high school where we started to be introduced to chemistry. And I didn't really know much about chemistry when I was younger, but then when I started to learn about chemistry and reactions, chemical reactions, and there was this like cool tie-in to both life and things happening in your daily life, but then also this mathematics of it too. Like it was a quantitative field, but it had a meaning that I could connect to real life, which I thought was really interesting. And so I got very excited about chemistry, and I had a really positive experience in my high school chemistry courses. And then when I got to college, I just started taking chemistry courses because they were my favorite classes and I enjoyed it. And at some point it's like, oh, well, I need to major in something. I'm going to choose chemistry. I also got involved in chemistry research when I was a freshman in college, and being introduced to working in a laboratory and being part of a research team was really exciting for me. And I also really liked that. And that was more of a materials chemistry research. So that got me really excited about chemistry of materials, which is now one of the themes that I work on in my group. So it's a whole confluence of factors, and ultimately just choosing what I enjoyed doing led me here.
How does chemistry, and in particular your research, apply to people's everyday lives?
One of the areas of research that we do is studying emulsions, which are droplets of one liquid dispersed in another. And emulsions are very ubiquitous in the products and materials that you come in contact with in your daily life. Great examples are in food, right? Anytime you have foods that mix water with fats and oils, you have emulsions. Milk is an emulsion, for example. A lot of personal care products are emulsions. And this ability to mix dislike things, right? We always learn, oh, water doesn't mix with oil, but a lot of the products, formulations, paints, coatings, lotions, food, gosh, so many things require you to mix oil and water. And so in order to do that, you can formulate emulsions by adding surfactants and soaps and stabilizers and things like that. And we are very interested in understanding the structure of emulsions, what's going on at the interfaces between an oil droplet and the water phase. How do surfactants, which are basically soaps, shuttle things across oil-water interfaces? And despite how ubiquitous this is, like everybody uses soap every day to wash their dishes and get grease off of the dishes. Like there's still a lot of fundamental questions about how this works. And so we do a lot of research on just trying to understand the basics of emulsion structure and dynamics and the chemistry and how that plays a role.
That's a good answer, I guess. And then also along those lines, what makes you excited to come to the lab every day?
I'd say there's two things, and both of those things are ultimately why I decided to pursue this job in the first place. One is it's just the joy of doing research and discovery and asking questions and being able to design experiments to answer them and contribute to growing our body of knowledge about the world and how it works, and to be inventive and creative and come up with new ideas. So there's that part that I really love. But then there's also the working with the people part. I enjoy mentoring, working with the graduate students and the undergrads in the group. There's the teaching aspect to that that is really enjoyable. So there's the people part, and then there's the science and discovery part, and both of those really contribute to this, to my really enjoying this job and what gets me excited to come into work every day.
As for your research, if you weren't in your current field of research, is there anything else that you would think that you would focus on?
Yeah, I mean, I can go back to my childhood passion of marine biology. I still love learning about that, and dolphins are just my personal favorite animal, and I think it would be really fun to. I always was fascinated about deep sea life. It's kind of like space exploration, but on our own planet, and all of the amazing creatures and ways that they've evolved to live in these very extreme conditions. I think that's fascinating. I am personally not brave enough to go in those deep sea submersibles and be the person that actually goes to do these things. But I think studying that would be really exciting.
If you weren't working in chemistry, is there a career path that you would have chosen?
I always enjoyed learning about law. I took some law classes in undergrad, and it's kind of a man-made science. And I think that's what I found appealing about it, right? And when we're scientists, we're nature, physics, there's fundamental rules that governs all of what we do. And then in law, I was like, oh, there are rules, but now they're all man-made. And so now you can think about how you could design the rules and the laws to then give you outcomes that you want to achieve in society. And I thought that idea was very interesting. And I enjoyed learning about law and the theory behind law, and also how that feeds into economics and actually using laws to get people to do things that are good for them and good for society. It's a way of pushing, like nudging people to make good decisions for themselves and the people around them.
Yeah, so I guess now for your teaching, if you could teach any class not chemistry related, what would it be?
I have a passion for creativity and creative thinking, and I've never done research in this. I know some people that do. I think the research is fascinating, and when I have more time, I would love to be able to learn more about this. And part of teaching a class is that you get to actually teach yourself the content first before you then go on and teach the class. And so I would love to learn more about how our mind works and how we solve problems and think about problems and how we creatively come up with solutions and how we can have more insight over our own thinking. And I would love to learn more about the current research in that field and then turn that into a class. So when people take the class, or when I'm teaching the class, I feel like I learn more about myself and the ways that I approach thinking about science and making decisions and solving problems, because I think that would give you tangible skills that you could then apply to different areas of your life to like make your own awareness of your own thinking enhanced.
Like the way that your thinking changes. And I think that's a really big thing for people to learn. I guess like one thing that people say with like getting a PhD is like you learn how to do research / like how to do things, not just what the chemistry is and whatever it is, but
Yeah, you learn how to think. You learn how to think. You learn how to solve problems creatively. I think a general issue with a lot of science education is that it's very fact focused, and here's an equation, here's how you use it. Here's some expression that describes the relationship between these objects, and you learn these things, and it is very quantitative, and it's very like prescribed, and you don't think about how that knowledge was created. You just take it as a given. And so a lot of people that like science and math, and myself included, were like very quantitative, and you think of it as not a creative subject. It's not like art. Oh, I'm just gonna paint whatever I want today and I'm gonna create something from nothing. But actually, when you actually become a scientist, that's what you have to do. Right? You have to take nothing and turn it into something, right? You have to create knowledge that didn't exist before. So it's science, I think, is a very creative process, but we don't teach it that way. And I think that maybe we lose out on a lot of talent in science because of that.
If you could teach any chemistry elective, I know like right now you're teaching the polymers class, but if you could teach just anything, even if you could make one up, what would you teach, I guess?
Well, I did create a new class, which I'm going to teach in chemistry for the first time next semester. So I don't know if that counts, but I did have the opportunity to create a new chemistry elective, and I'm going to be teaching a class on responsive materials, which is something that I really like thinking about, and that is related to our research. And the basic concept is, how do you make materials more lifelike? And thinking about the ways that you can couple chemistry to mechanics and the material properties. As chemists, I think we get very used to thinking about molecules in a reaction flask and the molecular scale, and we don't think very much about how do I take those molecular scale properties, reactions, bonding, etc., and actually use that in a functional way to affect macro scale material properties. So I think teaching that in a class will be really exciting.
What is one of your most unforgettable memories from your chemistry career?
I have a memory of when I had an idea for something to test, an experiment to do, and I went into the lab and I did it, and it actually worked the first time that I did it, and it almost never ever happens. And basically the context was, I was working with laser synthesis, laser patterning, and I wanted to be able to use the laser to synthesize and deposit platinum films, and nobody had done this before. And I was trying to think of a way to use the light from the laser and convert that, use that to synthesize platinum nanoparticles and deposit them on a surface. And I read about photography. I read about the chemistry of that was developed 100 years ago for converting sunlight into platinum nanoparticles that would then make up photographs. Most people are familiar with silver photographs, but people have developed chemistry for platinum and palladium and gold as well. And I said, I'm going to try to take this same chemistry, these same reactions, and I'm going to use this, but now with a laser. And it was a little bit more nuanced than that. We were also doing like a 2-photon process, so the wavelength of light was a little bit different. But anyway, that was the concept. And I mixed everything together, hit it with the laser, and nanoparticles were made before my eyes, and they were deposited on the surface. And I was like, wow, that nothing ever works this well the first time you do it. So that was a rare experience where things actually work as you hypothesize. Most of the time, things don't work out that way.
In honor of Women's History Month, who is the most influential woman or role model or professional, whoever it is, in your professional life, and why did you choose this person?
Well, in my professional life, it's probably my PhD advisor, Joanna Eisenberg. She was my PhD advisor when I was at Harvard. I was studying chemistry, and she is very well known and influential in the fields of bio-inspired materials and biomineralization. And she was always very supportive and inspiring. She was always so excited about chemistry and the research. And if there's one thing that I took away from her, it's that, you never lose that passion and excitement about the fundamental research. Like, no matter how hard it gets or the roadblocks that come up, you just never lose that excitement about what you're doing. Like, always make sure you're working on something where you see the light at the end of the tunnel, so to speak. Like, you could envision that exciting result or that end goal. And so she was always very enthusiastic and optimistic, and I try to be that way as well.
Yeah, that's a great thing to live by. So then, who's your favorite Nobel Peace Prize or Nobel Prize winner? And maybe in chemistry, it doesn't have to be in chemistry, but yeah.
Yeah, I don't know. I thought about, I read this question, I thought about it. And I don't have a great answer for it, to be honest. I mean, we do a lot with, polymers, and a lot of my graduate work was related to polymers. And obviously I think polymers are super cool now that I teach a class in polymers. And so I could say maybe Staudinger was one, he won the Nobel Prize for basically coming up with polymer being a macromolecule, which I think is pretty amazing and has had tremendous impact. But then more recently, we've had more, just recently, there have been several female Nobel laureates whose work is very different from mine, but yet I find very inspiring. And I've, like Frances Sarnell, for instance, I've heard her speak and give seminars a couple of times, which I think are always very, they're very inspiring. And to see women now making such a significant impact and being recognized with Nobel Prizes in their fields, I think is really exciting. It's hard for me to pinpoint one person, though.
Yeah, no, I agree. I also really like Frances Arnold, and I think I read somewhere that like right when she was like about to start doing her experiments, that someone said like, oh, like that's not science, like you can't be doing that. But then she did it, and then
that is a very similar theme. I've heard this multiple times. I've heard that from her. I also went to a talk from Jennifer Doudna, and she said something very similar, where it's like, I started this early on in my career and people told me to quit because they told me this is not going to be successful, this is not going to be impactful. But there was just something about this problem, she did all this CRISPR stuff, right? That's become so impactful, right? But at the time where she started working on it, it was not. And so you have to take this leap of faith, so to speak, in believing that what you think is exciting and interesting, it really is worth doing, even if other people around you say, oh, that's never going to work, right? You have to be willing to stick with it. And if you're excited about it, just do it, like no matter what other people think. And that's where probably most of the most revolutionary and exciting discoveries are going to come from, are the things that people think aren't going to work, and the things that are really surprising. Those are where the transformative discoveries are going to be made.
Yeah, so for our last question, this one's a little bit different, but so what is your most cherished chemical element?
Yeah, I don't know. I like fluorine. I think fluorine's cool because we do a lot of work with fluorinated solvents, and we're so used to thinking about hydrogens being bonded to carbon and the properties of alkanes and hydrocarbons, and it's just carbon, hydrogen, and a few other heteroatoms. But then we forget, oh wait, you can also have carbon fluorine bonds, and you start sticking fluorines onto molecules, and they have totally different properties. So for instance, hexane is not miscible for fluorohexane, You just take all the hydrogens, you replace them with fluorines, and now it has a totally different set of properties, and these oils don't actually mix with each other at room temperature. So I think fluorine is a very cool element because of our work with fluorocarbons, but there are a lot of other cool ones too.